So we'll start with tutorial 4 by the first lecture of this course. This blocks focuses on the fundamentals principles of wireless communications. As you know, wireless communication is based mainly on radio waves, which is a means for transporting data. In our case, the data that we will transmit is a digital data. We will not consider analog data for transmission. So we'll have only digital modulation in these blocks. Since most of today's applications rely on the digital encoding of data and not on the analog case. So most of wireless communication involves radio waves, and the words wireless and radio are often synonymous in our case. Radio waves are a particular form of electromagnetic radiation. Other forms include light, X-rays, and gamma rays. The term electromagnetic is used because all these waves involve the physics of electricity and magnetism. The wave travels as a result of a fundamental relationship between electricity and magnetism. A changing magnetic field creates an electric current, and a changing electric field creates a magnetic current. So an electromagnetic wave has these two fields orthogonal to each others, and both is orthogonal to the direction of transmission, as illustrated in the following figure. The time between successive oscillations of the radio wave is called the period of the wave and is measured in seconds. The number of complete oscillations which take place in a second is called the frequency. So as usual, we have the frequency, which is the inverse of the period. Okay, so when we say we have 2 cycles per second, as if we are saying the duration of a cycle is a half a second. So both period and frequencies are inverse to each other. So the major parameter used for wireless communication is the frequency, and the other important parameters that well describes the radio wave is the wavelength of the wave. Okay, the wavelength of the wave and the frequency are inversely proportional to each other according to the following formula: C equal lambda f. So C is the speed of propagation of radio wave. We'll consider it as speed of light as assumption. It could be not exactly equal to this value, but you can use it as equal to 3 times 10 to the power 8 meters per second. So this speed is equal to lambda f. So in our case, lambda f is equal to this constant speed, although it's not in reality constant. So lambda f is inversely proportional to each other in this case. So the higher the frequency of the wave, the shorter its wavelength, and the lower the frequency of the wave, the larger its wavelength. So this relation between lambda and f is very important and has an impact on the propagation of radio wave. So keep it in your mind. So to calculate the period of a radio wave whose frequency is 2 gigahertz, you should make the inverse of 2 gigahertz to obtain the frequency, and you should have the unit in to have the unit in second. You should transform the 2 gigahertz into hertz by multiplying it by 10 to the power 9. Calculate the frequency of a radio wave whose period is 4 milliseconds. So the inverse of 4 milliseconds provide you the frequency, and to obtain the frequency in hertz, you should transform the millisecond duration into second by multiplying it by 10 to the power minus 3. Calculate the wavelength of yellow light emitted from a sodium lamp if the frequency. So as you know, light is one type of electromagnetic waves having a specific range of frequencies. So within this range of frequencies we have the electromagnetic waves that you can see it as a human being, and outside this range of frequency we cannot visualize electromagnetic wave. So given a special case of yellow light having the frequency 5.10 times 10 to the power 14 hertz, if you would like to calculate the wavelength of such wave, we can use the equation C equal lambda f, and so lambda equals C over f. So as we have said, C should be equal to 3 times 10 to the power 8 meter per second. In this way we can obtain the wavelength in meters. So the motion of electrically charged particles produces electromagnetic waves. These waves are also called electromagnetic radiation because they radiate from the electrically charged particles. Radio waves, microwaves, visible lights, and X-rays are all examples of electromagnetic waves that differ from each others in wavelength. So we can say that this wave is different from another. This wireless transmission is different than another by its frequency or by its wavelength. So one can lead to the other. The electromagnetic spectrum is a term used to describe the entire range of frequencies of electromagnetic radiation from 0 to infinity. So spectrum represent range of frequency. Keep it in mind. Represent all range of frequency. Electromagnetic spectrum represent the whole range of frequency. Signal spectrum represent the range of frequencies of a signal. Okay, so spectrum is always a range of frequencies. So the electromagnetic spectrum is composed of different categories. Radio wave are the waves that have the wavelength greater than 1 meter or 1 millimeter. Okay, we have the X here in meter. So radio and microwave used in wireless communication have the wavelength greater than 1 millimeter, and then we have infrared radiation that have smaller wavelength between 1 millimeter and 1 micrometer, and then we go to smaller and smaller waves. For visible light we have wavelength in the order of fraction of micrometers, and then ultraviolet we have fractions of nanometers, and then X-rays and gamma rays we have very small wavelength in the order of atoms and molecules. So as you can see, we have wavelengths with different sizes, so it's obvious that not all these waves are appropriate to be used for communication, since we'll have from one side difficulty in propagation of the wave, and from the other side we are taking some risk that could be dangerous to human being when we have a wave with high energy in the order of molecules, atom and atom nuclear. So such waves could be very dangerous to human beings. Even the other waves with high power could affect the health of human being. So the wavelength that have the waves that have a wavelength appropriate for radio communication are those for microwave, denoted by microwave and radio wave, that have the wavelength of greater than 1 millimeter. So if we use the equation C equal lambda f to check what are the radio frequencies appropriate for wireless communication, then you can for 1 millimeter for wavelength equal 1 millimeter, we can obtain f equals c over lambda, and this will be equal to 3 times 10 to the power 8 divided by 10 to the power minus 3, and this will lead to 300 gigahertz. So for wavelength greater than 1 millimeter is equivalent to frequencies less than 300 gigahertz. So these category of waves are appropriate for radio communication. Okay, the frequencies which are greater than the other frequencies, this means the frequencies that are greater than 300 gigahertz, these waves have a wavelength smaller than 1 millimeter. These are not appropriate anymore to use for wireless communication, except infrared, which is used in some small range communication. The other ones become too small and inefficient and even dangerous to be used for wireless communication. So the among the microwave and radio waves, we will have different bands, different frequency bands, and then we will distribute different channels in each band, and we will compare the different frequency bands based on the frequency and wavelength. So as we have said, the lambda f is equal to the speed of propagation. This means that these two parameters are inversely proportional to each other. So we should know very well that low frequencies, low frequency waves have long wavelength, and high frequency waves have short wavelengths. So we'll have the frequency band of used for wireless communication from very low frequency to extremely high frequency, and it only deals with the RF, means radio frequency portion of the spectrum. So each decade is defined by defined frequency band, often referred to by name, from very low frequency VLF at the bottom up to extremely high frequency at the top, as you can see here. The region above 1 GHz, which includes EHF, SHF, and part of the UHF, is commonly called the microwave spectrum. Terminology is not completely consistent, however, and some authors regard microwaves as beginning at 3 GHz. These wavelengths range from 100 km for 3 kHz down to 1 millimeter for 300 gigahertz. So as you can see, we have very low frequency from 3 kilohertz to 30 kilohertz, where wavelengths change from 100 kilometer to 10 kilometer. So these very long waves were used for military navigation, marine communications. Low frequency range from 30 kilohertz to 300 kilohertz. Wavelength range from 1 to 10 kilometers. These long wave were used for radio broadcasting, navigation, and time signals. Medium wave MF from 300 kilohertz to 3 megahertz. Wavelength range from 100 meter to 1 kilometer. These medium waves were used mainly for broadcasting signals. And then we have HF band from 3 megahertz to 30 megahertz. Its wavelength range from 10 meters to 100 meters. So these HF bands were used also mainly for radio broadcasting and communications. And then we have very high frequency VHF, which ranges from 330 megahertz to 300 megahertz, wavelength from 1 to 10 meters. And these waves are mainly used for mobile and air communications and for DAB broadcast and FM radio broadcast. Then we have UHF band from 300 megahertz to 3 gigahertz. Its wavelength ranges from 100 millimeter to 1 meter, and these are used for analog and digital data, digital TV broadcasting, mobile phones, Wi-Fi, radars, and microwave ovens. Then we have SHF super high frequencies from 3 GHz to 30 GHz. Its wavelength range from 10 millimeter to 100 meters, and these are used for mobile phones, Wi-Fi, WiMAX, radars, satellite broadcasting, mobile microwave links. Finally, we have extremely high frequency EHF from 30 GHz to 300 GHz, and its wavelength ranges from 1 millimeter to 10 millimeter, and these are mainly used for satellite broadcasting and radars. So each frequency bands includes some typical wireless application area, from military and navigation applications at the lowest frequency up to satellite communication and radar at the top frequencies. If two radio waves are transmitting on the same frequency or on two frequencies that are very close, then their signals get mixed up. There is interference between them, which can be heard as voicelets, distortion, or mixed up sounds. And spectrum management is required. In the UK, the spectrum is coordinated by the National Frequency Planning Group, who issue a frequency allocation table from time to time. So the frequency band or bandwidth spread over a range of radio frequencies is called the bandwidth. Okay, generally speaking, the more data that is conveyed by a signal, the larger is its bandwidth. Okay, So to transmit more data, to have higher bitrate for our wireless communication application, this requires higher frequency band. Keep it in your mind, because we'll see it clearly later on when after studying the modulation techniques. So video signals generally require a much greater bandwidth than speech signals, and so on. Channels interference is avoided by ensuring that the bandwidth of a signal does not overlap with an adjacent one. Each frequency band can only cope with a certain number of signals. To provide an adequate bandwidth for each signal and to avoid overlap, many application bands are structured into specific or specified channels. So we'll have a specified channel for each user per application, okay, and we'll have a band for each application to avoid interference among different applications, and then we'll have different channels for different to avoid interference within the same band of the same technology, because we have 48 channels as it is given. By dividing the band into 48, we can obtain the channel band, and then we can, once we obtain the channel band, we can calculate the lower and higher frequency of each channel, starting from channel 21 and ending by channel 68. So instead of using individual channels, the separate signals all share the whole of the allocated band of frequencies in the case of spread spectrum. So this is an alternative technique to transmit data. Instead of transmitting over a specific channel, we can use spread the spectrum techniques, as we will see in the coming weeks, by learning frequency hopping spread spectrum and direct sequence spread spectrum. So we'll see with FHSS frequency hopping spread spectrum used in Bluetooth. Each signal rapidly hops from between a large number of narrow channels in a predetermined and unique sequence. Each signal is sharing the same channels but is hopping in a different sequence. As long as the receiver knows this sequence, then each signal can be recovered individually. Direct sequence spread spectrum. Here, each data bit in a signal is modulated by a unique and very fast binary code, which causes every signal to occupy wide frequency band. If the receiver knows the code that has been used to spread a signal, then this signal can be picked out from all the others, even though they all occupy the same wide frequency channel. Ultra-wideband spread spectrum technologies for short-range, very high data rate applications, such as distributing high-definition HD video signals within a home. These are generally known as ultra-wideband (UWB). In the USA, low-power UWB devices are at present allowed to occupy the entire range from 3.1 GHz to 10.6 GHz. We'll see more details. About the UWB technology in the coming weeks. This is possible because the energy of each UWB signal is spread so thinly over this range that any conventional transmission within it are relatively unaffected. However, various technical approaches to UWB have been put forward by rival commercial interest, and the standard has yet to reach. The early days of radio broadcasting and communication were centered around the LF and MF bands. Most of the current applications relevant to this course are in the VHF, UHF, and SHF bands. This trend to higher frequencies is expected to continue, as you can see in the following examples of applications: as onboard vehicle radar with high frequency bands 24 GHz, 76, 77 GHz, radar vehicle 24 GHz, satellite broadcasting 10.7 and 12.8 GHz, microwave ovens 2.45 GHz, IEEE 802.11 wireless local area network Wi-Fi 2.4 GHz and 5.7, Bluetooth 2.401, UMTS 1.8, 2.11, 3G systems 1.88, GPS 1.228, GSM 880 to 960, analog and digital TV broadcasting 470 to 854, as seen in the previous example. Digital and audio broadcasting 217.5 to 230 megahertz. Marine police ambulance taxis 138 to 173, 425 to 468, civil air band 118 to 137, FM radio broadcasting 88 to 108, short range low power devices, keys, alarms 27, 47, 50, 173, etc. Wireless audio devices 863 to 865, model control 27, 35, 40, 454, CB radio 27, 28, short wave broadcasting and communication 2.3 to 30, medium wave broadcasting, long wave broadcasting, RFID, and the order of kilohertz, hundreds of kilohertz, MSF standard time signal for radio controlled clocks 60 kilohertz. We have licensed and unlicensed band. Unlicensed bands are a bit of a free-for-all in which finding an unused channel cannot be guaranteed. However, there are regulations which specify maximum transmitted power so that any interference effects are local. This is appropriate for short-range equipment such as Wi-Fi networks, cordless headphones, and digital phones. The use of licensed bands involves paying a fee for the legal right to use certain frequencies, and these are controlled much more closely. Mobile phone systems and broadcasting fall within this category. Log scale is very important in telecommunication for many reasons, and we will have many formulas later on that use log scale. So it could be good to review the mathematical functions of log scale, because we'll need its features later on. So logarithms and log graphs come up several times in this course, thus we need to make an overview of this mathematical scale. And log scale is commonly used to minimize the large scale representation of power ratios and frequency ranges. So as you can see, we have log of any base b equals 0 when x equal 1. So log of 1 is equal 0. Log of x is negative when x is between 0 and 1, and log of x is positive when x is greater than 1. Log of a multiplication m times n is equal to log of m plus log of n. Log base 2 of 2 power n, for example, is equal to n. Log base 10 of 10 power n is equal also to n. Commonly used radio frequencies range from 3 kHz up to 300 GHz, which is a large factor of frequencies. Because of this large range of frequencies, it's useful to represent frequencies graphically on a logarithmic scale. This, the interval which represent a factor of 10 change, such as between 3 and 30 and between 30 and 300, are called decades. Multiplicative increase in frequencies correspond to an additive increase in the log scale. A ratio of power P2 over P1 can be evaluated in dB using the expression 10 log base 10 P2 over P1. So decibel is a very important unit used for power representation. So it's a logarithmic calculation of the power ratio multiplied by 10. So in this way we have a more compact range of values. So when we have a negative value of decibel, this means that the power ratio is less than 1. We have attenuation of power. We have attenuation which is due to transmission. When we have a 0 decibel, means that same power ratio is equal 1. When we have the power in decibel is positive, this means the power ratio is greater than 1. This means we have amplifications and so on. The ratio of powers can be, for example, received power at some station divided by the transmitted power by some station. Output power from an amplifier divided by the input power to the amplifier, etc. An amplifier which increases signal power by 1000 times is said to have a gain of 30 dB. If the signal power is reduced by a factor of 1000, then you can say that this is a loss of 30 dB, or alternatively a gain of minus 30 dB. However, you may also come across sources which refer to a loss of minus 30 dB. The bottom line is you should always know whether the signal is getting bigger or smaller and interpret the plus or minus signs accordingly. dBm is used to avoid very small numbers. The ratio of power is relative to 1 milliwatt P over 1 milliwatt. The power in dBm in this case is equal to 10 log base 10 P over 1 milliwatt. This means that 0 dBm is equivalent to having the power equal to 1 milliwatt. And each additional 10 dBm represent an increase of 10 times the power. So 1 watt is 30 dBm and 1 watt is minus 30 dBm. Consider the transmission of a signal having the power 200 milliwatt. Calculate the received power in microwatt if it's equal to minus 50 dB. So minus 50 dB equal 10 log base 10 of P2 over P1, which is equal to 100 milliwatt. In this case, log base 10 P2 over P1 is equal minus 5, and then we raise 10 to the power from the two sides of the equation. 10 to the power minus 5 is equal P2 over 200 milliwatt, and in this way we can calculate the received power. Calculated microwatt, the power of signal is equal minus 50 dBm. So minus 50 dBm is equal 10 log 10 P2 over 1 milliwatt. So minus 5 dBm equal log base 10 P2 over 1 milliwatt. We raise 10 to the power from the two sides of the equation. 10 to the power minus 5 is equal P over 1 milliwatt. So in this way we can obtain the received power value.